This meeting is being recorded.
So, hi everyone. Before jumping into this third order response function, I just want to make few statements. We know whenever we sorry, whenever we think about spectroscopy or whenever we picturize a spectra, the tendency of our mind takes us to think in terms of quantum mechanical theory. Like we think about discrete energy levels and we think about how a transition is made from one energy level to another and how transition dipole moments are connected to this spectral response. But in classical mechanics, things are a bit different. Here we don't have discrete energy levels, and so the spectra that is simulated using this classical MD mainly depends upon the dipole moments that changes or the changes in the dipole moment that is induced due to the change in configuration. So in the year 1950s, mainly Green and Kubo gave some relations which connected the response functions to the time correlation functions. So that will be probably discussed by someone else. With this in mind, I want to move into today's topic, that is third order response function for collective modes. So whenever I'm saying collective modes, it means that we are not tagging a particular bond or a particular molecule, but rather we are interested in what is happening in the whole system. So the response function for such modes can be evaluated by various methods. However, today we will be focusing on two, and I will be first discussing this equilibrium molecular dynamics approach, and then we will be talking a bit about NEMD. So in both the cases, it involves correlation functions of dipole moments or either its derivatives. But as Himanshuda already discussed, he discussed the linear IR response functions, where you saw that there was the response function was a correlation between two time correlation function. Here in third order, we will be seeing multi-time correlation functions. So here, uh, the proper quantum mechanical description of third order response function is given by this equation. My cursor is visible, right?
Yeah, it is visible.
Yeah, okay. So the third order classical mechanical response function is given by this expression, which involves three commutator bracket relations. Now, the evaluation of this response function is obviously not possible. So we are going to basically come into the classical limit, where we will be replacing this commutator bracket with the Poisson brackets. And the commutator bracket and Poisson bracket are related with this relation, where we know that Poisson bracket can be given by commutator bracket and multiplied by 1 by IH cross. So here I've just substituted the commutator bracket with the Poisson brackets. So here you can see there are three Poisson brackets relation here. And classical mechanically, this Poisson brackets can be solved. Suppose we have two dynamical quantities, x and y. So this Poisson brackets can be solved by taking partial derivative of these quantities with respect to position coordinate and momentum. Now,
Rimpi,
yeah.
if this Poisson bracket is just this multiplication of this bracket with 1 upon iota x cross, then how does it changes its property?
How does it?
Changes its property. Like you said, it's difficult to evaluate this bracket, square bracket, but if we go into this Poisson bracket thing, then it can be solved. But it's simply multiplication.
No, because we quantum mechanical description or the like evaluating a response function quantum mechanically for the whole system is not feasible. We know that. So we want to come to this classical mechanical description. So I'm just replacing the Poisson bracket here. In fact, this is also not the expression of the response function that we'll be using. We know that it will get simplified and we will come up with better expressions.
Okay.
Yeah. So here I've just written this rho EQ, which is the equilibrium space density matrix, or also the probability distribution, equilibrium phase space distribution function, which is given by e to the power minus beta h0. And now the thing will be like, it's a bit handwritten note, so please bear with me. So now this three Poisson bracket terms, we will be solving this one by one to make our response function look a bit better, because solving multiple Poisson bracket computationally is not feasible. So yeah. So we start one by one. So we see that the first Poisson bracket term is between this rho EQ and mu 0. So we just put in the formula, we take partial derivative of these quantities with respect to position and momentum. And you can see that it comes up like this. And this within the square bracket, you see this is again a Poisson in the form of a Poisson bracket. So you can write it as H0 and mu naught. And from Liouville's theorem, we know that the time evolution with respect of a dynamical quantity can be represented in terms of this. So mu dot 0 can be written as Poisson bracket of mu 0 h0. So that's what I have just substituted here. So this is the whole idea. So one by one, after getting this expression, one by one, we solve this three Poisson bracket equations. So it becomes a bit messy, but however, like you see here, we apply the same thing. We again and again we are going to take derivative with respect to position and coordinate and try to simplify our equation. So the main thing is, after solving the second equation, the term appears to be something like this. So lastly, we come to this final evaluation of this Poisson bracket. And yeah, it finally your response function takes a form of like this, which can further be simplified by taking separate traces of these terms. And finally, we come to an expression that looks like this. So I'll be sharing this PDF, and if you see any mistakes or if you want to look at it, you can tell me. So the main thing is, earlier the response function contained multiple Poisson bracket terms, but now you can see the response function have been simplified to contain a single Poisson bracket term. Now still there is one Poisson bracket term which needs to be evaluated. Somehow that is better than solving multiple Poisson brackets. So the question is, how do we evaluate this Poisson brackets? Because we know that whenever we are doing a classical MD, we do have system dipole moments at multiple times. So taking its derivative and taking a 4-point time correlation function is not a very hard task. However, the computational evaluation of this Poisson bracket is not that straightforward, because you can see this Poisson bracket are now involving time as their are function. Sorry, this Poisson brackets of this dipole moment are going to be functions of time, and those times are also not very straightforward. They are at different, means they are not same, like they are different at different intervals. So
These are Rimpi. These are not absolute times. No, these are time
No,
difference.
these are all simulation time. These are all simulation time that we take, like we have, if we have a single trajectory. So if we consider point 0, then relative to that, you will get T1, T1 plus T2 and all.
No, but are these absolute times? I think these are these time intervals.
No, these are relative time.
These are
Like,
relative.
yeah, these are relative time.
Yes, okay.
The
Yes,
same
yes.
thing that we did in, the evaluation of 4-time correlation function. That is the same thing. So, in the year 2006, mainly, or 2005, no, sorry, in the year 1998, Shinji Saito actually solved this Poisson bracket terms. And how he did it was he assumed certain conditions. Like he said, the dipole moment is a function of position only. And since he was not considering any polarizable model, so there was no charge fluctuation in his case. So this Poisson bracket term can be now given by this. Now, since dipole moment is a function of coordinate only here, the evaluation of this del mu del p is not straightforward. So we will be, he used basically chain rule in there, where he said that del mu del p can be given in terms of del q del p. So this seemed quite feasible when I first thought about it. But again, it seems things are not that simple. So, uh, so here's the question. When I said we are going to evaluate this Poisson bracket terms, now everything is a function of time. So this when you are taking this dipole moment and taking its evaluating its Poisson bracket, which relation is actually correct? Is it like del mu del q at 0 and del mu del p at t, or it should be like del mu del q at 0 and del mu del p at 0? I hope I'm not confusing you, right? Okay, anyway. So seems like in this paper which I was following for this, they used this relation where they took the Poisson bracket in terms of del mu del q 0 and del mu del p 0. And this basically now follows this chain rule, where you see that the position of a particle at time t is getting influenced by change in momentum of that particle at time 0. So again, computational evaluation of these things involves transformation matrices like Jacobian, and he used this Jacobian matrix and evaluated at each and every point along with this coordinate and momentum. He evaluated this matrix where he saw how is this del q del p is going to vary with time.
Rimpi,
Mhm.
could you please again explain this mu zero mu t or mu zero mu t expression? I just lost it. Like I couldn't
This
understand
one,
what were you.
this
This
one.
one, this one. Yeah.
Yeah, so basically, I was saying in Poisson bracket that I showed you how it's evaluated, you take partial derivative with respect to position and then momentum and then vice versa. You just exchange them. So the thing is, now we are talking about partial derivatives, but there is also time dependence in it. So
Okay.
when you will be taking this partial derivatives, here del mu at 0 is getting a partial derivative with respect to its coordinate at 0 time. But what
Okay.
I thought that del mu at t we will be deriving it partially with respect to the momentum at time t, but things are not like that. It's mainly del mu at 0, del mu at q 0, and then the second term that you're getting is taking the partial derivative at partial derivative of momentum at time t with respect to the partial derivative of dipole moment at time t with respect to the momentum at time 0.
Okay. So you're thinking to apply both of these, or the other one
No.
is correct and what was? No.
I'm not thinking of applying it. I'm telling you what he have done in his paper.
Okay, what
So
he have done in his paper. Okay.
yeah,
Okay.
so
Okay.
like how he evaluated this partial derivatives to actually get the Poisson bracket terms.
And both of these equations are equivalent.
No, those are not equivalent. That's what I was trying to say.
Okay. Fine. Go
Yeah,
ahead.
because you see, the function is different. Like
The
here,
function is.
hmm.
Oh, okay.
Rimpi,
Go ahead.
Mhm.
Rimpi, what is the basic difference, physical difference between these two relations you have written now? These two,
Physical difference. You don't see any. Like, what do you mean by physical difference?
but what is the physical justification of this Poisson bracket, this relation you are using?
Mm-hmm.
At that momentum is taken at 0, and but dipole moment at t, and also the second term that substituted. They are all three terms in time t, but dipole moment in 0.
Actually, it's like whenever in force field based simulations, whenever we're doing, where we get at different points of time, we get the coordinates of different atoms and momentum of different atoms. There certain kinds of algorithms are followed. For example, velocity world algorithm and others. So there you see this whenever you're calculating the coordinate of the atom at time t, you need the old coordinate at time 0. Along with that, you are taking the velocity into consideration for calculating the coordinate of your atom at time t. So here the thing is, whenever we are doing this numerical partial derivatives, things are like not that straightforward that you will take change in coordinate. Matlab you just can't do a numerical subtraction at time 0 and time t, because a slight change in momentum of the particle at the backward time will definitely create some change in the coordinate of your same particle at final time. So that's the thing, the physical significance comes there. This partial derivative is going to be like this instead of this. I might be wrong, but I think this is the thing.
Okay.
Okay.
Rimpi,
Hmm.
when you evaluate any Poisson bracket,
Hmm.
like we evaluate Poisson bracket at a certain basis, right? Like QP or Q prime P prime. So in the first equation, when you are evaluating Poisson bracket between mu0 and mu t,
Yeah.
what is the basis here?
Here
Q0 PT
yeah.
or
No. I already said here he have taken into assumption that the dipole moment is a function of position coordinate only. So it's just q0.
yeah,
And time
dipole
0.
moment is a function of coordinate, that is fine. But I'm saying
Yeah.
that the basis like Q0 P0 or QT PT you can use, right? But it seems like this is the mixed basis. Q0 PT and P0 QT, both bases are, both terms are there. So it should be like, I don't know, it should be like Q0 P0 or QT PT, right?
Yeah, that's what I was trying to explain. This second expression is the right one, right?
No, let's first focus on the first equation.
Okay.
In the first equation also, if you just assume that the basis is Q0 P0, then what would be the Poisson bracket? Like del mu0 del Q0, del mu t del P0, then del minus del mu0 del P0, and del mu t del Q0, right?
Okay. Yeah.
If the basis would be Q0 P0, And
Okay.
if you use QT, then it would be like del mu 0 del QT, del
Okay.
mu t del PT minus del mu 0 del PT, del
Mm-hmm.
mu t del QT, right?
Okay.
But
So you're
it
saying
seems
I've
like
mixed
it is
it.
kind of it is a kind of like mixed, right? Q0 PT, P0 QT,
Hmm.
all the four terms are there. So both
Okay.
bases are not equivalent, like Q0 P0 and QT PT are related by Jacobian transformation, right?
Hmm.
Both bases are not equivalent. So that's that's where I am confused actually. So it is
Okay.
a kind of mixed basis or not? Like I don't know. So
Actually, in the paper, he used this chain rule, this second one, del mu del p at 0. So, taking this in mind, I just thought he must have taken the Poisson bracket equation like this.
yeah, I understand his actually motivation, but
Hmm.
fundamentally I'm actually confused. Okay, I
But
look
one
into the
thing,
paper.
Hmm.
in that Poisson bracket, that
Hmm.
0t, the function of time, these are not the absolute time. So I think the
Hmm.
time difference is important. So
Hmm.
in that way, Q0, P0 and PT, QT, these are the different thing or the same basis?
That must be the different thing, right? It is the pure dynamics is happening. So let's say Q0 P0 initial condition, and after some time T, QT PT is the final position and momentum. Then both position and QT PT are related to the Q0 P0 by a Jacobian transformation.
Mhm. Hmm.
Okay,
Then in
so
that case,
that's
there will
true.
be four basis, four
Yeah,
time
yeah.
basis.
Mm.
Hmm.
Okay, I'll look into it. I
Yeah,
just told
that
you like why I considered this equation. That was my thought process because I just back calculated things should be like this since he's using this chain rule.
yeah, that is fine. Yeah, it is fine.
Yeah.
Okay, we can go ahead now.
Yeah.
Hello, Rimpi.
Hmm. Hmm.
One more thing, like to go in the previous slide, or there is one approximation you did. This one,
Okay.
this approximation.
Ha ha ha.
This one is dipole moment is said that is a approximation of that coordinate, like generalized.
Like
There is
yeah,
a
they assumed कि
why
dipole
it's
moment.
approximation. Dipole moments is a function of coordinate. No? So
Yeah, but
why?
we know that dipole moment is like charge into the distance r. That will be
Hmm.
depending on coordinate. But
Yes.
when we are taking, suppose in our case, when we are using this polarizable force fields,
Hmm.
the charge q, that's capital Q in this case, because let's not confuse things. So
Hmm.
that does not remain constant, right?
Yes. Hmm.
Yeah. So then in that case, in our case, basically this mu should like here he is taking it because he's used this rigid model. But if you take polarizable model into considerations, then capital Q will also change and dipole moment will become a function of capital Q, small q and t.
So for that case, you can say that's an approximation. But
Hmm.
is this approximation word used by Shaito sir?
No, he
Or
used assumption, assumed.
assumed. So
Yeah.
I don't get like why this assumption required in that particular case. I don't get that.
Mm, why it's required?
Why this assumption?
Like from his point of view, when he already knows it's rigid, so why is it?
Front of view, because diplomat is a function of coordinate, we can say. So there we don't need any assumption or approximation. I don't get like why this assumption.
Okay.
One more related question that Q here this in this paper he used the rigid model, then dipole moment only the dipole moment change only vectorial sense, not means in terms of magnitude it will be constant. Means you are talking about this total collective dipole moment or single particle dipole moment here? Collective dipole
Maybe
moment.
collective.
Actually,
Maybe
collect.
collective.
here or
yeah,
everything
then
is about collective.
yeah, then then they are in this model. This is exact. The dipole moment only change function of positions.
Yes,
Hmm.
so
Okay,
that's
in
why
this
I'm
model,
talking.
this is exact. But approximation means that dipole moment means this is the main factor. Okay, that's why he can model this way. Means from this rigid model, he can calculate dipole moment from this rigid model. This is the approximation. Means if this does not function of Q strongly,
Hmm.
then this kind of rigid model
Hmm.
means collective based on collective uh, collective moment. Okay,
Hmm.
that does not work. So this approximation is necessary.
Okay.
And
No, I
another,
didn't get Vamshida, like why
no,
it's
if
necessary.
this approximation does not hold,
Hmm.
okay, then we cannot calculate this collective moment from this rigid model.
Okay.
Okay. Because
Okay,
of this
that's why.
approximation, we can, yes.
Okay.
Means I am thinking another more point that like Skinner's approach or others approach, the mapping approach, which they are also dipole moment means those model does not work only, does not limited to the rigidity of our particle. Okay, non-polarizability of our particle. They are also this charge fluctuation is connected to the environmental coordinate of all the particles. So there also this dipole moment is function of position. Means we actually we can model the charge with the position of all the particle in the system. There also means where this approximation would not valid in strict sense. That is a good question. Means where means this approximation was not valid when this electronic dipole moment is electronic response. Okay, this electronic response does not could not be captured totally by the coordinate only. Then only this approximation would not valid. Okay, so finding such examples where this dipole moment means this could happen in some in case of most probably canonical cross section where this nuclear coordinate to potential to electronic potential are very close. Subodhi might comment here more. They are this kind of strict dependence of this dipole moment with the coordinate would not be valid there.
And in the case where, like, you already know, Deepika Di and Shimanshu have done this data thing. So, whether this assumption will be valid in their case?
Yeah, assumption will be valid in their case. This assumption will valid also Skinner's case.
So then you are saying I can take this. So I can take this assumption and like try to go ahead with this.
For our case, this is perfectly well, but this works perfectly well. But I am thinking where this approximation would not be valid means there will be a major part coming from others influences.
Because
that might happen when
we generally talk this is as an approximation. We take in granted these things. Like this
That's what I am thinking. Yes. That might happen when this electronic response does not could not be calculated from this nuclear position, instantaneous nuclear position. So that could be one case. And yeah, this your second part, this boson mutuality. This is basically, I think, this is a technical thing. How do we calculate this boson bracket? This Subodip also.
Yeah, actually, I now get it. I think because it is the Poisson bracket between quantities at two different time. So that's why they are just using this type.
Means it is a technical thing. Both are, I think, both are correct. Both expression.
but they're not
How do we
equivalent.
calculate this? Yes. How do we calculate this?
Yeah,
That's why
they are not
they manage.
equivalent. The value will be different, of course.
Yeah.
Yeah. And yeah, regarding that assumption approximation, actually I didn't get it. What was the question?
You're saying why did I use the term approximation? Because
No,
Shinji
what was
Saito
the approximation?
Shinji Saito sir didn't use the term approximation. He said he is assuming that dipole moment is a function of only coordinate here.
Acha, acha. Hmm.
Okay. But the thing is, evaluation of this matrix, this DJDT, it's very like computationally costly. And what Shinji Saito sir did is he wrote his own program where he used because in force field based simulation we generally use integrator that are already available to us by the software. But here he used his own program and he basically used a sixth order integrator, symplectic integrator. I exactly don't know what it is, but how will I do this if it's possible to do it?
Now, CSI to calculate this method means with application of electric field in different direction.
No, that is the NEMD approach that I'll discuss after this. That is a different approach he applied again, but that is in 2005 that we're talking about. But before in 1998, he used this EMD approach where he calculated these matrices. And he said, though it was for only 64 water molecules, and if you take large number of water molecules, things will get very complicated.
Yeah, it seems numerically.
Yeah, it's very. And he also mentioned it is going to be numerically unstable since we are calculating second derivatives. So the error factor.
Yeah. So they did not mention any simplistic way.
No, after this, that's why in order to save our computational cost, and he moved into this non-equilibrium molecular dynamics approach.
Okay.
Yeah. So in this approach, this is more easy to connect with since it resembles experiments. Because in experiments, we know that there is this pump probe spectroscopy. We apply lasers and we get response. So in a similar fashion, in the simulation also, he applied electrical fields and basically got the response. So before moving into the expression of the response function, okay, so here the basic assumption that we take is the external field that is applied is weak. And by using this commutator bracket relation, the first order response function can be simplified by using this expression, substituting it in here, and then we get this expression where we get this response function is going to be an ensemble average at time t. So this is the ensemble average of our total dipole moment of the system at time t in the presence of electrical field minus the ensemble average of the dipole moment of the system in the absence of electrical field. Now, in the similar fashion, this third order response function can be actually derived, but I haven't showed that here because it's going to take time. Anyhow, even then, if you see, basically in 2DIR experiments, what we do, we apply 3 electrical laser pulses. One is at time 0, we apply a pump pulse. Then at 2 different times, T1 and T1 plus T2, we apply 2 probe pulses. So in a similar fashion here, what they did, they you can see here are 1, 2, 3, 4, 5, 6, 7, 8 terms. So they needed to run 8 different simulations where they applied the electrical field at these times, and at every expression you see here, this is the total ensemble average of the dipole moment of the system in presence of the 3 electrical fields. This is in presence of 2 electrical fields and so on. And this one is the normal one where there is no electrical field applied. Even then, we need to calculate 8 trajectories, and that is also again computationally costly, but less costly than the calculating those Poisson brackets and Jacobian. So in the year 2006, Tanimura came up with a better third order response function for collective mode, where he
Hello,
had,
Rimpi.
Mhm.
Sorry to stop, but I didn't get this 8 simulation things and this thing. I didn't get.
Okay.
Just
So yeah, okay, 1 minute. So in normal Hamiltonian mechanics, we know that this q dot, which here I've represented by r dot, is given by del h by del p, right? Where h is the Hamiltonian, and this p dot is given by again del h by del q, which is our force that we take. Don't take into consideration the second things that I've written. Now here the thing I wanted to discuss this later though, but this is the basic of NEMD simulation that in normally here the Hamilton's equation of motion are not followed. Here we see extra terms in NEMD for calculating the coordinates and momentum. These extra terms where Ri and this gradient of u, which is the velocity gradient, is also involved. So when you're like, what was your question? Like, why do you need to run 8 different simulations?
yes, that was my question.
Yeah, the thing is, since I already said it's this NEMD simulation thing is going to resemble the experiments. So we know that in the normal simulation that we do, we are not applying any electrical field. So there is no question of perturbation there, right?
Yes.
Yeah, so that is a normal equilibrium, the thing that we get, the 2-point correlation function or anything, that is our normal thing, that this expression, this thing that we get. Okay. But you know, in a typical 2D experiment, what I was telling, we apply a pump pulse, then we apply again a flow pulse, and again a flow pulse. So similar kind of analogy is used by this NEMD thing, that they will be applying 3 electrical pulses, and then they will be seeing how this how our trajectory has changed with respect to that, and this at different times, because we want to see what is the effect on the total dipole moment of the system after applying 3 electrical pulses. We don't want to take into consideration the coupling that is happening because of the other pulses. So they
Okay,
have
so then one thing, they applied 3 electrical pulses in 3 different simulations.
3 different simulation or 3 different simulations. You need 8. You need 8 trajectories. You can see there are 8 terms here.
In this R3 expression?
The non-equilibrium method that I've written, there are 8 terms here. So you need 8 trajectories. Because why I'm saying 8 trajectories? Because every ensemble average is different. It is a function of different times.
Okay.
Yeah. So the matrices will be that you will be evaluating will depend on this.
So then this thing is clear, but like the electric field what we applied, so that is in the same direction or in the different direction, like in the x direction, y direction, in same direction, or simultaneously in 3 directions?
Yeah, so that is the question, and that is what I wanted to discuss mainly here, because that is where
so then fine.
Yeah.
So Rimpi, one thing, in that your R3 expression, so so this is all average dipole moment, right? Every term, just all those
Yes, yes,
eight
yes. Ensemble
terms,
averaged all
those
average.
every means
Huh, huh,
average
huh,
dipole moment.
huh.
But but average dipole moment, don't you think like sometimes it may be zero if
But
you
here you have applied an electric field. You're not
yeah.
considering equilibrium conditions. So,
So, okay, continue.
yes, so
Uh, okay.
Okay, Himanshu, then continue.
Yes, Subhajit. Yeah, I'm done.
Okay. So then the question is like what you told, like this 8 term corresponds to your 8 different simulations.
eight
So
different trajectories.
8 different trajectories. Okay. So then if I consider the first term only, the mu T3, T2, T1, so that depends on what you read in the after this ensemble average, like T2 plus T1 and then T1 and 0. Huh. But the dependence of this mu, what you wrote, that's a T3, T2, and T1. Huh. Correct. So I didn't get this one. Like, what's the corresponding?
These things are these three times are related here. Like you see, like the T1 time is this, T1 plus T2 time.
Huh, I got it. Like T1, T2, T3, these are the delay times. Like after how many times, how much time you applied the your electric pulses. Huh. So how your these terms, these in the response function, these mu terms, huh, so that every mu terms is depends on T3, T2, and T1. Huh. But again, you write this T2 plus T1. So that that value. So if you see, like the first one is T2 plus T1, then T1 0. The second one is T2 plus T1 and T1, and the third one is T2 plus T1 and then 0. Okay. And again, what happens? So this is 0, this is T1. So this, okay, so we'll discuss it later. So
Yeah, if you want me to derive this, it will take time firstly, and secondly, this is a well-established equation. Like
no,
people have already used it. It's not like I've written it on my own.
so maybe I'm not able to connect, like
It's
so
like
we'll
this,
discuss
like
it. Huh?
What are you not
the
able to connect?
Like I'm not able to connect like your 8 different trajectories with you want to connect with this expression. So that I'm not able to connect. So maybe we'll discuss it later. We can continue.
I think Sojit's question is that means you apply those pulses, means non-equilibrium method means you apply different electric field, means electric pulses, means T1 means this 3 time window, means this 3 time point means you apply 3 pulses at 3 different times.
Exactly.
0, T1, T1 plus T2. Here you apply 2 pulses at 2 different times, T1 and T1 plus T2, second term means.
Yes.
And the towards the last term, we can see that there is only one pulse. So I think this is the Sojit's question, that we apply different pulses at different time and calculate the average mu at T3 at means at longer time.
Detection
Okay,
time.
at the detection time. So we calculate from different non-equilibrium situation. We calculate the average mu and just put it in the expression.
Okay, so that means like if I consider the third term, so that means there are only 2 pulses are there at
Yes,
0 time and T1 plus T2 time.
Yes.
Okay, so
Yeah.
Okay, so that means this is not constant that in every simulation you applied 3 pulses.
No, that will change.
So that's why I'm asking this point. No, I'm not getting.
Yeah, actually, the simulation part, that is the main thing that I wanted to discuss today, because that
Okay,
is where
fine.
I'm stuck.
I
Yeah.
got it.
Okay, okay. So in normally we all know what is EMD simulation. We all do it. What we do is take our initial configuration. We take our system, how many, whatever we want to take, whatever molecules we want to take. Then we basically do energy minimization, and after that we do some NVT and NPT equilibration. Now the thing is, and then we do the production run. That is the main schematic of our EMD simulation. But what is different in NAMD that I have that I've realized after reading is the initial configuration that you take in case of EMD. Here we come to this step where we have equilibrated the system, and after that, uh, from here we take the initial configuration. That is our the starting point of NAMD simulation. And here what we do, from taking that configuration after the equilibration, we apply this external electric field and carry out our simulation. Now the question is how this external electric field is applied in terms of simulation. The thing that I was showing is this is one approach where the equation of motion have changed. Like you can see there are constraint terms here with the velocity gradient. So now this velocity gradient term will actually include this effect of electrical field. This velocity gradient term is given by this matrix element where this H0 is a parameter that you can control, and this delta T is the strength of the electric field that you want to apply. So in 2007 that or 8, Shinji Saito sir did this NEMD simulation where he used this delta T value as 0.1 electron volt per angstrom. And Shubhajit's question, like how we will be seeing like this directions thing for different case will actually like that is what my confusion lies also. Like here you can see the off diagonal elements x, y and yx direction. Here they have taken it as non-zero. So here in this paper they said ki, the this is something related something to shear rate where they talk about viscosity and all. I'm not pretty clear about this, the direction thing. I don't know.
Delta U is external electric field. Delta U.
Delta U is the velocity gradient.
Okay.
Yeah. So now the equation of motions that we will be evaluating that will give us our coordinate, momentum, and other various dynamical quantities will actually follow this equation of motion instead of the previous Hamilton's equation of motion. And this delta U term actually contains that external electrical field strength.
Okay, this is H0/2.
Yeah, at this H0 is a parameter that is constant and you
This
can
is
control it.
it depends on the strength of electric field.
Actually, in the paper, he have not exactly mentioned about this matrices and all.
So
Maybe
this is the
because
first
this
time used by Saito sir, or they
no
used
this
any
NEMD
other
approach.
method?
This NEMD approach is established. Like they have many people have used it, not only used by Saito sir. So that's why he have obviously not explained the whole thing. But
So this delta U thing and this thing, so there is not any proper proper clarification thing on any other paper or not? Like they have cite any paper?
mm,
Like suddenly they come up with this velocity gradient thing as well.
This suddenly say the thing is they in the paper that Shaito sir have done, he have just written NEMD approach or NEMD simulation. Okay, even there he didn't mention anything about this. This is what I have read about NEMD, and I think this is the thing that might have been followed by him.
Rimpi, show the P dot term. Just scroll down once. Yeah. So, okay, let's just assume one thing. Just a simple model. Okay. Just previous Hamiltonian was, let's say, harmonic oscillator p square by 2m plus half omega square q square. Then you are applying an electric field, let's say, okay, along the coordinate. So now the Hamiltonian will be just harmonic oscillator plus or minus q times e, right?
Yeah, there will be one E, or you can say
Yeah,
mu
just
E, but because dipole moment
yeah,
is
just
there.
mu.
Yeah.
Let's say mu is q, so minus q times e. Okay. So now if you write down the Hamilton's equation of motion, it will be just q dot will be just p by m plus del H del p plus there will be no terms, right? Because e is just a function of t and it is multiplied with q. So there is no momentum term here.
You're
But when
saying
you
about this minus pi into gradient of u.
yeah, I'm
It
just
should not be
thinking
there.
about the no, should not be there. That's I am thinking about the simple model term, like how the total Hamiltonian will look like.
The total Hamilton, like H0, you can
Yes,
take
let's say
yeah.
yes, H is the total Hamiltonian, right? H0 minus epsilon mu del T. So from this Hamiltonian, if you write down the Hamilton's equation of motion, let's say, so R dot will be equal to del H del P, right?
Yes.
Del H del P. So it will be just first term will be P by M, and in the second term epsilon mu del T, there is no P term, right? There is no momentum term here.
No.
So from the second term, there will be no momentum contribution, right? So R dot should be equal to just P by M.
Okay.
And P dot will be equal to del H minus del H del Q or del H del R. So first term will be equal to minus del H0 del R and the similar term, previous term. And from the second term, mu is now a function of R. So that's why you will get minus plus del mu del R. So minus epsilon del mu del R del T you will get, right?
Okay.
If you just think about the normal Hamilton's equation of motion.
Yeah, I got your point.
Yeah, so that's why I'm thinking, like, how did they get?
In fact, I actually thought about this, even like dimensionally, it wasn't matching. But this is like, I have not written it on my own. This is in the paper. I
Yeah,
will share it with you.
Okay, right.
Okay, so that's it. What I wanted to basically discuss, and was
Related
thinking
to Swadip's
Hmm.
question, that is there any form of Hamiltonian they have written?
Yeah.
So
This
the Rimpi
should
showed
not,
just.
this would certainly not the Hamiltonian. Means for
Yeah.
this kind of yes, means
Yes.
there it looks like velocity coupling, momentum coupling. In the expression of P dot.
According to the expression of Hamilton's equation of motion, there should be a momentum coupling also.
Yeah. Means in that equation of motion. Go to the next slide. Yes. That P momentum coupling, for the momentum coupling in the last equation, P dot equal to F minus. It means that there is momentum coupling in the model.
Okay.
So, and yeah, you pointed out correctly that delta U is something like shearing force.
But
This
Vanshika, here I was thinking this expression, like this whole equation, it's like dimensionally, is it matching? Like I wasn't able to do it because here you see it is the momentum per time derivative. So it's meter per second square, and here also it is force, and then it is dVdr. Like dimensionally, it's not matching, but there in the paper they have written it. I'll have to check again.
No, we can use reduced dimension. That is, but here is delta U. If we think means delta U, there have some there we can see some explanation. Means delta T is the electric field. Okay, means electric field along x direction means will change the
Due to
velocity along
y direction.
y direction. So this kind of things happens if we apply electric field in a there is a dipole in space. Okay, and if we apply electric field, DC electric field, then there the dipole will feel torque.
Okay.
Okay.
Dipole moment means only na dipole will feel torque. Means dipole moment. That only means na there is a torque.
Yeah, dipole. I am not talking about. I am talking about particular a single dipole, not collective one.
Okay.
That single dipole means how the shear force will come. This the single dipole, if we apply the electric field in x direction, okay, if there is point charge, it will move. But if there is a dipole, not point charge, a point dipole, the positive point tends to move outward and negative point moves to point inward. So it feels torque. So from there, this velocity gradient might appear. So I think we need to find out the Hamiltonian expression. Then it will be much more clear. In the Hamiltonian, how delta U, how this torque-like term appears in the total Hamiltonian.
So nowadays, in this softwares, we have certain features. Like in Chromax, there is a feature that where you can externally apply a field by just using a command. So similarly, there is a feature in Tinker as well. But the thing is, they don't exactly mention how the electric field is applied, like the direction or anything.
There, the electric field means it just add with the total force. Means initially force are the intermolecular interaction. Then that considering each point as a point charge. Okay, each atom has a point charge. They just add the total energy. They contribute to the total energy into charge multiplied by field. Okay. So in that way, the simulation, the protocol is same there. Means the equilibrium equation of motion is always same. Just the form of the energy will change there.
Okay.
But here, why did they model in different way? Means this delta U. Means if we consider the point charge, then I think your previous Hamiltonian equation would works. But why they use this kind of thing means this kind of thing appears for me maybe appears due to the point dipole. Means point charge, the expression would be similar. Okay, we will.
Actually, in the paper, they never mentioned that they have used this. Okay, so they have just mentioned NEMD, and this is what I read about NEMD. And there he mentioned that he has used this delta t term as 0.1. So that's what I assumed he must have done something like this. Now, in order to get proper clarity, then I would like have to mail him to get to know what exactly I've done.
Yeah, we have to. We will discuss more why they choose this thing, this model, not the same Hamiltonian expression with the new force, including a extra term in the force or energy. Okay, you can. Means I think basically Shinji Saito did not use any package. Do not use any package.
No, he don't use any package.
Yes. I think that's why he tried to simplify as much as possible the numerical calculations. Okay.
And does anyone know how this numerical numerical calculation of partial derivative system?
Partial derivative, yeah, I did the finite difference method. But this is the very basic thing.
Yeah, that's for complex partial derivation that will be not accurate enough.
Okay.
Yes.
So there is no way to
And no way
actually.
means we generally use partial finite difference. I also use finite difference method. But
Okay.
There are for integration. There is means I did some trial calculations on this Gaussian quadrature approach means to approximate it better. If you take finite difference, then when the curvature is much higher, then there you get much more error, and where curvature is very low, so there you can take the larger difference. Okay, so in that way, means there is a generalized approach like Gaussian quadrature, like that. There you can efficiently and accurately do this kind of integration. This is one approach.
Okay,
There are others.
you can do it.
Yes.
Actually, Rimpi, there is a just a recent article just got published 2 days ago, I think, from Deepak Oza. I think you will know the vibrational dynamics of liquid water in an external electric field. I think they also did similar kind of non-equilibrium study there, so you can look into it. It's a JPCL article.
Okay, recent paper I also skipped. Okay, we will discuss. Okay.
So I'll stop sharing.
Okay, Vamshit, I can stop the recording.